Welcome to The Explainer. Look, if you've been tracking the frontier AI space for a while, you know the drill. Unchecked, rapid-fire release cadences from the top research labs used to just be the norm. But as the data from June 2026 clearly shows, that era is entirely over. Today, we are going to dive deep into a massive structural shift, the transition from OpenAI releases to sovereign, state-vetted infrastructure. And we'll examine how that macro shift is forcing radical, ground-up changes all the way down to custom silicon and the edge compute software layer. Let's get right into it.
June 2026 was a massive wake-up call for the industry. The traditional mechanism of distributing frontier model weights completely shifted. We went from simple open API access to a highly politicized, state-supervised deployment paradigm. Basically, model weights are now being treated, both legally and strategically, like nuclear or military hardware. It is a completely different playing field.
And 30 days. That is the new baseline we have to operate under. Driven by a national security framework established by the Trump administration, the federal government instituted a rigorous 30-day vetting window. Federal agencies now have a full month to evaluate the national security and cyber exploitation risks of advanced AI models before they can even see the light of day. So here is our roadmap for today. We're breaking this down into 5 key areas: the sovereign AI era, custom silicon economics, encoder-free multimodal edge models, production-grade developer tools, and finally, physical AI deployments. Starting off with Section 1, the Sovereign AI Era, focusing on national security and blackouts. Let's take a look at the macro geopolitical forces now actively dictating these model releases. Just look at how this played out in June. This timeline perfectly captures the reality of the new regulatory environment. On June 9th, Anthropic announced Claude Fable 5. It was a massive model featuring a native 1 million token context window. Huge news, right? But just 3 days later, on June 12th, the U.S. Department of Commerce invoked direct export controls, forcing a global blackout of the model. And the reason is wild. Amazon researchers discovered Fable 5 could actually be bypassed to identify complex zero-day software vulnerabilities and generate operational exploit code. Obviously, not exactly what you want a public chatbot doing. It took an 18-day blackout, working right alongside the government's Center for AI Standards and Innovation, to train a highly specialized safety classifier. They finally managed to redeploy on June 30th, and that updated system now automatically falls back to the older Opus 4.8 engine if it flags any coding task as potentially unsafe.
But Anthropic was definitely not alone in feeling the pressure here. OpenAI previewed its next-generation GPT 5.6 SOL model, which showcased a staggering 6-fold improvement in quantitative biological reasoning. However, at the request of the Trump administration, its release was restricted to a whitelisted cohort of just 20 government-vetted enterprise partners. Meanwhile, the sheer volume of pressure coming at the industry from all sides is just staggering. On the corporate espionage front, Alibaba deployed 25,000 proxy accounts to execute a 28.8 million query distillation attack on Anthropic, attempting to siphon reasoning pathways for Chinese domestic models. And legally, we saw Florida file an 83-page civil lawsuit against OpenAI and CEO Sam Altman. That suit cites severe negligence and harm to minors, demanding verified age gatekeeping. It's a multi-front battle right now.
Moving right along to Section 2. Custom Silicon Economics, Engineering for Auto-Regression. Let's shift our focus down from regulatory policy to the physical infrastructure required to sustain these massive compute demands.
$20.92 billion. Let that sink in. That staggering figure is OpenAI's operational loss for fiscal year 2025. And that's despite generating over $13 billion in revenue. The main culprit? The sheer unsustainable cost of running auto-regressive inference, which is essentially generating text 1 token at a time on general-purpose NVIDIA GPUs. Standard graphics processors are built for parallel workflows, things like 3D rendering or physics simulations. For large language models, which basically just repeat forward passes through a transformer network, that generalized architecture results in massive overhead. It's just not financially viable long-term.
So, OpenAI's response to this financial bottleneck was radical. Partnering with Broadcom and Celestica, they designed Jalapeño. This is an application-specific integrated circuit, or ASIC, and it's an absolute beast, an 840 square millimeter die, pushing the absolute physical limits of EUV lithography, the bleeding edge of microchip manufacturing. But here's the genius part. Rather than standard multiprocessors, Jalapeño uses a systolic array layout. That's a grid explicitly designed to stream model weights in perfect lockstep with transformer attention kernels. By co-locating high-bandwidth memory directly on a shared interposer and utilizing Broadcom's Tomahawk fabric for rack-scale interconnectivity, Jalapeño promises a 50% reduction in total cost of ownership compared to legacy GPUs.
All right, Section 3, Encoder-Free Multimodal Edge, the software layer. As centralized inference scales to the absolute breaking point, we are moving up the stack to see how edge models are being radically re-architected. Historically, traditional multimodal models relied on separate, pre-trained encoders. You'd have something like a 550 million parameter vision transformer and a 300 million parameter audio conformer, all crunching data before finally passing it to the language model. Google DeepMind's Gemma 412B Unified entirely changed the game here. They stripped away those separate encoders completely. Now, raw 48 by 48 pixel patches and 40 millisecond audio slices are linearly projected straight into the exact same shared embedding space as the text. It's an incredibly clean, single, unified decoder-only backbone. The impact this unified architecture has on local inference is incredible. By utilizing 4-bit standard quantization, known as Q40, the open-source community managed to shrink the Gemma 4 12B model from nearly 27 gigabytes down to just 6.7 gigabytes. Think about that for a second. This allows developers to run a state-of-the-art, 12 billion parameter multimodal model completely offline right on a consumer M4 Pro laptop, and it achieves 42 tokens per second with just an 8.4 gigabyte VRAM footprint. That is a total game changer for local development. And for those who need to fine-tune these edge models for specific domain tasks, the math is incredibly efficient now. Using quantized low-rank adaptation, which is a highly efficient fine-tuning shortcut, developers utilized a rank of 16 and an alpha of 32. This targeted just 65.6 million trainable parameters. Running this on a single, mid-tier NVIDIA RTX A4000 GPU took exactly 28 minutes and cost about 7 cents in compute time. The result? That fine-tuned adapter achieved a 100% score on context verification. You can now reliably steer complex edge model reasoning on highly limited local infrastructure for literal pennies.
Which brings us to Section 4, Production-Grade Developer Tools, Terminal Native Execution. Let's zoom in on the actual interfaces developers are using to orchestrate these models.
We are so far past browser chat boxes at this point. With Anthropic's Claude Code, we've moved into agentic terminal native tools. When initialized, it generates a project-level Claude.md briefing file, acting as long-term project memory for the AI. But more importantly, developers are now hard-coding strict permission barriers directly into their local repositories. You can configure the JSON settings to explicitly deny the AI the ability to edit sensitive files, like your .env configuration. You can also establish deterministic post-tool use hooks, so anytime the AI edits a file, the system automatically triggers your project linter to run on that specific path. It's safe, structured, and highly automated.
And to govern these autonomous loops, prompt engineering has completely matured. We've moved away from simple conversational instructions to deterministic, multi-step XML reasoning traces. What you're seeing in this code snippet is a blueprint for a decomposed agentic validation loop, specifically used for red teaming. It essentially forces the model to execute a self-ask decomposition step, output a transparent reasoning trace, evaluate its own proposed changes against prompt injection vulnerabilities, and finally deliver the code refactor in a strict JSON schema block with zero polite conversational filler. This entirely bypasses sycophancy patterns, that annoying tendency for the AI to just politely agree with the user, which was so common in older prompting structures.
Finally, let's hit Section 5, Physical AI Deployments and Advanced Manufacturing. Let's see how all this advanced logic and custom silicon crosses from clean code directly into heavy industry.
This pipeline is literally how you manufacture the future. TSMC has integrated NVIDIA's accelerated GPU computing libraries right onto their factory floor. They use the cuLitho library to run optical proximity correction simulations, achieving a massive 20 to 50% cycle improvement. They use QES to accelerate material chemistry calculations by 50 times. And out on the physical fab floor, inline camera sensors feed real-time visual data straight into NVIDIA Metropolis models. This natively automates nanometer-scale defect inspection on active wafers, entirely eliminating those massive manual verification bottlenecks. The quantifiable results we are seeing across heavy industry are just stunning. Siemens Energy is utilizing NVIDIA supercomputers to run massive neural network simulations of physical turbulence for low-carbon hydrogen gas turbines, reducing their overall computational design times by up to 77%. Meanwhile,
ABB Robotics and Psionic are taking human manipulation datasets collected during bioprosthetic research and using them to train real-time neural feedback loops for industrial robotic arms. This is granting collaborative robots unprecedented human-like dexterity. They can dynamically adjust grip force from millinewtons all the way to high pressure, allowing them to handle highly delicate items on fulfillment lines without crushing them.
So, wrapping this all up, the landscape has fundamentally shifted. We've gone from open API playgrounds to custom silicon built explicitly for autoregression. We have unified edge models running locally on our laptops, and physical AI is literally driving semiconductor fabs and robotic arms. With AI now heavily regulated as a sovereign asset and integrated so deeply into our physical factories, the question is no longer how fast we can scale, but how securely we can control it. It's absolutely something to think about as this new, highly structured era unfolds. Thanks for joining me on this deep dive.